Hello, good evening, class, and welcome to the technical class on transformer design. And basically, we are going to do some problems on transformer design, which is in your syllabus also, and they are good question. Okay, so we were working on this question, and in this question was asked like estimate the reduction in volume expressed as a percentage of original volume of iron core conductors in a transformer when hot rolled silicon steel lamination worked at a flux density of 1.2 Weber per meter square is replaced by cold rolled grade oriented silicon steel lamination worked at 1.8 Weber per meter square. Circular coils are used and the thickness of winding is negligible as compared with diameter of circumscribing circle. The length of flux path, area of conductor, and the number of turns are the same for both cases. Okay, right? So what is asked in this question is that you have a transformer which is having a iron core made up of hot rolled silicon steel lamination, and the flux density of this core is 1.2 Weber per meter square. You want to replace the core with the cold rolled grade oriented silicon steel, CRGO steel, and whose flux density is greater, that is 1.8 Weber per meter square. So when you will replace the material from hot roll to cold roll grain oriented silicon steel, you will increase the flux density, and this way you will actually reduce the amount of iron used and the amount of conductor used. Okay. So what you have to find is to find the how much amount you will reduce and estimate the reduction in volume expressed as percentage of original volume. Okay. So this question we were discussing, and we have already solved for the first part, iron core, and what we found that we were able to reduce the uh, amount of net iron area reduced was 33.3%. Okay, so we did solve this question. Okay, we did solve this question earlier, and what we found was that by using the ratio of the flux densities, we can actually find the ratio of the uh, iron core, right? And to find the ratio of the iron cores, we got AIC by AIH, the ratio of the iron core area of cold rolls steel lamination divided by hot roll steel lamination was equal to 0.667. Now only we need to find the reduction, so we will subtract from AIH minus AIC divided by AIH into 100. That is 1 minus 0.667 into 100, and this way we got 33.3% reduction in the net iron area. Okay, right. So we did the reduction in volume, and from this ratio of AIC by AIH, we found the reduction in net iron area was 33.3%. Okay, so I hope you have taken the notes. Now the second part we shall have to do, we have to find the reduction in volume for conductors. Okay, so let me share. Yeah, so I hope you are able to see the screen. Now reduction in volume for conductors. Okay, so this we are going to do today in this session of the class for the electrical machine design. And it's a very good question, and I hope you will enjoy this class. Okay, so reduction in volume for conductors. Okay, and for this we need to assign two variables, d of h and d of c. Okay, and you let me tell you the question which we are doing. So this was the question which we are doing. Estimate the reduction in volume expressed as a percentage of original volume of iron core conductors in a transformer when hot rolled silicon steel lamination worked at a flux density of 1.2 Weber per meter square are replaced by cold roll grain oriented silicon steel lamination worked at 1.8 Weber per meter square. Circular coils are used and the thickness of winding is negligible as compared with diameter of circumscribing circle. The length of flux path, area of conductor, and the number of turns are the same for both cases. Okay. Right. So first part we have already done. We have solved the iron core problem, and we found that the reduction of volume in the iron core was 33.3%. Now we have to find the reduction of volume for the conductors. Okay. And you should remember in this question that it is given that the circular coils are used. So circular coils must have diameters. Okay. So even if you are using the hot rolled silicon steel lamination, they have circular coils, so there will be diameter for that. And for the cold roll grain oriented silicon steel also, there will be circular coils, so there will be diameter for that. And thickness of the winding is negligible as compared to the diameter of the circumscribing circle. Okay. So we can ignore the thickness of the winding. The length of flux path, area of conductor, and the number of turns are the same for both cases. Okay. So keep this in mind. And then let us move to the whiteboard. Okay. So we are assigning here. What we are doing here is we are assigning two variables, d of h and d of c. And d of h is the diameter of circumscribing circle with hot rolled laminations. And d of c is the diameter of circumscribing circle with cold roll grain oriented steel. Okay. Now, what we have to do is we need to use the formula for diameter of the circumscribing circle. Okay, so from the text you can refer to your Ike Shawnee. The chapter is transformer design. The diameter of circumscribing circle, diameter of circumscribing circle is actually proportional to root of the area of the iron. Okay, diameter of circumscribing circle is proportional to the root of the area of the iron. AI is the area of the iron. Okay, and we know that the relation between AIH and AIC, isn't it? You can just write down AIH by AIC is equal to 1 by 0.667. Okay, or you can write here that AIC by AIH we have derived earlier in the previous class was 0.667. Now you can just take the root of this. So under root of AIC by AIH, okay, will be equal to under root of 0.667, right? And this will be the ratio of DC by DH. Okay, this will be the ratio of DC by DH. True. Okay, so it's a very good relation that the diameter of circumscribing circle with CRGO divided by diameter of circumscribing circle with hot roll lamination is equal to root of 0.667. Okay, so we can just write that DC by DH, DC by DH is equal to root of 0.667, which is actually equal to okay, to just calculate this. Let us calculate this. What is the value you will get here is okay. So 0.667, and we need to find the root of that. So okay, so it is around about 0.8167. Okay, it is around about 8167. Okay, so the root will be equal to 0.817. Okay, so that means you can write your DC is equal to 0.817 into DH. Okay, now we need to find and also we know that the length of mean turn is pi d. Okay, that means pi times the ratio 0.817. Okay, so reduction in volume, what will be the reduction in volume? Reduction in volume for conductors will be actually equal to DC minus So it will be dH minus dC divided by dH. That is equal to 1 minus dC by dH. Okay, into 100 here to put. Okay, into 100. Okay, in percentage. So this will be equal to 1 minus 0.817 into 100. So that is equal to around about 18.3%. Okay, 18.3%. So this is the answer for the second part. Reduction in volume for the conductor. Okay, reduction in volume for the conductor is actually equal to 18.3%. That's a good reduction. So 18.3%, that much of copper you will reduce. So that will be a saving in copper. Okay, this will be the savings. This will be the savings in copper. 18.3% copper you will able to save. Okay, by using the CRGO. So you should always remember that CRGO, steel lamination, CRGO steel lamination is better than hot rolled steel lamination for a transformer core. Okay, and you are able to save iron and save copper. Okay, you are able to save iron also, and you are able to save copper also. And that is around about 33% of iron you can save, and around about 18% copper you can save. That's a very good thing. Okay, right? So this was our question. And that was our first question in transformer design, which we have done. And I think by next class we will be will try to solve the second question. Second question is, show that the output of a three-phase core type transformer is Q equal to 5.23 FBM HD square HW into 10 to the power minus 2 kVA. So we have to derive the output of a three-phase core type transformer in kVA. Q equal to this relation we have to find 5.23 FBM HD square HW, where F is the frequency and given in hertz, and Bm is the maximum flux density Weber per meter square. D is the effective diameter of core in meter. H is the magnetic potential gradient in limb ampere per meter. HW is the height of limb in window. So this is also a good question, and I hope you will enjoy this question also. Right. Show that the output of a three-phase core type transformer is given as Q equal to 5.23 FBM HD square HW into 10 to the power minus 2 kVA, where F is the frequency in hertz, Bm is the maximum flux density, in Weber per meter square. D is the effective diameter of core in meter. H is the magnetic potential gradient in limb ampere per meter. HW is the height of limb in meter. Okay, it's a good question, and we shall be solving this question. The question is also given in your book A.K. Shawnee for machine design, so you can refer that book also. And these question might come in your examination also. So I hope we will be able to solve this question, and we will solve this question in the next class only. It's an easy question. You just have to find the output of a three-phase core-type transformer. Okay, in terms of this variable, right? And already you know how to solve these types of question. Okay, because you have already done this topic of transformer design, and you know that kVA output kVA output of a three-phase transformer. kVA output of a three-phase transformer is given by this relation Q is equal to 3 into E I into 10 to the power minus 3. Okay, and you know that Q is also equal to 3 into, what is E? The EMF induced for a three-phase transformer core type is 4.44 into the frequency in hertz into flux density, flux phi m, maximum amount of flux, into number of turns into I, the current, into 10 power minus 3. Elaborating this expression, you can write Q is equal to 3 into 4.44 into the frequency into the magnetic flux density Vm into the area of iron core into number of turns T into current I into 10 to the power minus 3. Okay, it's in kVA. All these values are is in kVA. Okay, kilowatt ampere. And you should remember that in core type transformer, in a core type transformer, each limb has one primary and one secondary winding, and one secondary winding wound on it. And therefore, if you want to find the total magnetomotive force over one limb, so this will be equal to 2 times number of turns into current I. Okay, so we shall be using this expression also to solve our question. Okay, so I hope we shall continue this topic, this question in the next class, and I hope you enjoyed this lecture. For today this is enough, and I wish you all the best. for your upcoming exams, midterms, and all. And try to be attentive in the class, try to attend the classes, and be at home, be safe. And we shall be doing more problems on transformers. Thank you very much. Right, all the best. Goodbye. You can leave the class. Bye.